Welcome to This Explainer. We are about to take a high-speed road trip straight through the fascinating world of Unit 2 data transmission. We're going to trace the exact journey of a digital message from the very moment you hit send on your device all the way to the second it safely and accurately arrives at its destination. It's a journey that happens literally billions of times a second all around us, but most of us never really stop to think about the insane logistics making the whole shebang possible.
So let's quickly pull up our travel itinerary. We're breaking down the 5 essential steps of sending data: shrinking and packaging data, the rules of transmission, the magic of USB, catching transmission errors, and finally, keeping data safe.
All right, kicking things off with Section 1, shrinking and packaging data, getting ready for the road.
Before we can even think about putting our data on the digital highway, we've got a massive logistical problem. Our files, they're simply too big. Think of it like packing a moving truck. We need to shrink our items down and box them up efficiently using compression. And we've basically got 2 choices for packing our digital bags here: lossless and lossy. With lossless compression, the algorithm groups repeated patterns together so absolutely no data is lost. Every single original bit is perfectly reconstructed later. That's absolutely crucial for things like text files or spreadsheets, right? Losing even 1 decimal point there would be a disaster. On the flip side, we have lossy compression. This actually permanently eliminates unnecessary bits of data. There's no way to get the original file back, and it does reduce the overall quality. But it's totally perfect for MP3s or JPEGs, where our human eyes and ears won't even notice the missing pieces.
Okay, so once our data is shrunk down, we still can't just hurl it as one massive boulder. Instead, it gets chopped up into smaller, bite-sized chunks called data packets. This is the foundational concept of packet switching. Instead of sending one giant file, we send these small, independent units of data across a network, trusting them to find their own way to the finish line, where they'll be carefully reassembled at the receiver's end.
If we mentally rip open one of these metaphorical envelopes, we can see exactly how a data packet is structured. It's highly organized. First up, we've got the header. This contains the critical routing info, the IP addresses for both the sender and receiver, the sequence number so it doesn't get put back together out of order, and the size of the packet itself. Then we have the payload. That's the actual precious cargo or data being sent. And finally, it's all sealed up with a trailer, which includes an end-of-packet identifier, plus some really clever error-checking tools we'll dive into in a bit.
Now, letting these packets travel independently, it's a real game changer, with some massive pros but also a few cons. The advantages are huge. You don't need a dedicated single line of communication. If a network node is busy or fails, the packet just routes right around it. This means incredibly high transmission speeds and a system that's super easy to expand. But it's not perfect. Packets can and do get lost in transit. It's also prone to causing jitters in real-time streaming, and there can be a totally noticeable delay at the receiver's end while they sit there waiting to reorder all those randomly arriving packets.
Moving right along to Section 2, the rules of transmission. Time to navigate the digital highway.
So our packets are boxed up and addressed. Now they need to actually hit the road. But this highway isn't some chaotic free-for-all. There are very specific traffic rules. First, we define the direction of flow. Think of simplex transmission like a strict one-way street. Data flows in one direction only, like sending a document straight from your computer to a printer. Then we have half-duplex. This is a two-way street, but it's a super narrow bridge where only one car can cross at a time. Data flows both ways, just not simultaneously, exactly like a walkie-talkie conversation. Finally, we've got full-duplex. This is your massive multi-lane freeway, where data zooms in both directions simultaneously, just like your broadband internet connection.
Aside from the direction, we also have to pick our road type. Serial transmission sends one single bit at a time over a single wire. It's slower and meant for smaller data sizes, but because it only uses one wire, it's a much cheaper option and incredibly reliable for long distances. Think telephone lines. On the other hand, parallel transmission acts like a multi-lane highway, sending several bits, usually a whole byte, down several wires all at exactly the same time. This is lightning fast and used when speed is absolutely necessary. But because it requires way more hardware, it's expensive and really only works over super short distances, like the tiny internal circuits inside your computer.
All right, Section 3, the magic of USB, the universal connector. The physical act of connecting our devices to these digital roads usually comes down to one piece of tech we literally all use every single day: the Universal Serial Bus, or USB. Underneath its familiar, simple exterior, a USB cable cleverly uses an asynchronous serial data transmission method. And it does this using a shielded cable containing just 4 distinct wires. It beautifully isolates power and data. 2 wires are dedicated solely to providing power and an earth ground, while the remaining 2 wires are used exclusively for zipping that data back and forth.
It's honestly really easy to see why USB became an industry standard. It's incredibly user-friendly. You plug it in, and the device is automatically detected. The plugs are purposely designed to only fit one way, completely preventing you from making incorrect connections that could fry your hardware. Plus, it supports different transmission rates and is wonderfully backwards compatible. However, it does have its limits. The transmission rate for a standard USB is generally less than 120 megabytes per second, and because of signal degradation, that cable can't be longer than about 5 meters.
Moving into Section 4, Catching Transmission Errors. Let's talk about potholes on the road.
So, we've perfectly prepped our data, chosen our roads, and plugged in our cables. But what happens if our data hits a pothole out there? The harsh reality of computer science is that interference happens. Electrical spikes, radio interference, or even just faulty wires can cause bits to flip randomly from a 1 to a 0 or vice versa. Errors occur. So to combat this, we've developed some seriously ingenious, automated methods for catching these mistakes the absolute moment they arrive.
One foundational method is the parity check. This basically counts the number of 1 bits in a byte. By setting an extra parity bit, the system ensures the total number of 1s is always even or always odd. But a simple check like that has a flaw. If 2 bits flip, the error goes completely unnoticed. That's where the parity block matrix comes in, visually solving this problem. By adding extra parity bytes to create a grid of rows and columns, a computer can track parity in 2 directions simultaneously. If an error happens, the intersection of the faulty row and the faulty column points the computer to the exact single bit that flipped during transmission. It's like a giant puzzle solving itself.
Another fantastic mathematical solution we use is a checksum. Whenever a block of data needs to be sent, the sender runs a specific algorithm on the data to calculate a checksum value and attaches it right to the packet. After the journey, the receiver takes that exact same data and calculates the checksum again using the exact same math. They then compare their newly calculated value with the one that was sent in the packet. If those 2 values don't match perfectly, boom, they know instantly the data was damaged and they request a resend of the entire block. Now, what actually governs that whole process of asking for a resend? That relies on automatic repeat requests, or ARQs. Think of it like a super strict delivery driver. The receiver checks the data, and if it's flawless, they send a positive acknowledgement back to the sender. Meanwhile, the sender is operating on a strict timeout clock. They wait a set amount of time for that thumbs up. If they don't get it before the timeout expires, maybe the data corrupted or the packages vanish entirely, the sender doesn't even hesitate. They just automatically resend the data all over again, ensuring literally nothing gets left behind.
And finally, Section 5, Keeping Data Safe, Locking the Package.
Through error checking, we know our data isn't physically damaged, but we have one last massive hurdle: security. How do we ensure hackers aren't just reading our private data while it's cruising across these public networks? The solution is encryption. It's the process of taking our readable data, which we call plain text, and turning it into an unreadable scrambled mess known as ciphertext before it ever even hits the network. If a hacker intercepts our data packet on the digital highway, all they are going to see is absolute gibberish.
And we lock this plain text using 2 main strategies. Symmetric encryption is pretty straightforward. It uses the exact same key to both encrypt and decrypt the data. Both the sender and the receiver have to share this key. But, passing a secret key around over the internet can be pretty risky. So for way greater security, we use asymmetric encryption. This brilliantly uses 2 different keys. There's a public key, available to absolutely everyone, which is used just to lock the box. But to actually open the box and decrypt the message, you need a completely separate private key, which is heavily guarded and only ever held by the receiver.
It really is a total marvel of modern engineering. So the very next time you stream a movie, save a file, or just send a quick text to a friend, take a second to appreciate the incredible, flawless journey your data just took. It shrank itself down, split into perfectly labeled packets, navigated complex traffic rules, raced down parallel highways and USB cables, constantly checked itself for errors using brilliant math, and locked itself completely away from prying eyes, literally all in the blink of an eye. With billions of these encrypted packets flawlessly navigating our networks every single second, it really makes you wonder, as our need for speed and security grows exponentially, what on earth will the complex data highways of the future look like? Thanks so much for joining me on this explainer, and keep questioning the tech around you.